Hi guys, welcome to Learn Electronics Repair. I have here a power supply out of a powered mixer, and I was looking at this on a previous video. So we have a hole burnt in the PCB here. In the previous video I figured out that there is a 95 volt track, actually minus 95 volt track, that passes through this area and goes off eventually to the connector at the end, the one I've removed. So the track goes all the way from here to these large resistors here. The circuitry in the area that is burnt is actually on a 17 volt supply, plus and minus 17, and that supplies this op amp chip and the LM393 that I've taken out of here. Before I repair this damage, I want to know whether this chip is any good. This is a dual op amplifier. It's a fairly typical one, BA4560. There's many different dual op amplifiers on the market, and I don't have this one in stock, so I need to order a replacement for it, which will take a little while to get here. And it would be good to know whether or not this is actually faulty. It's possible that the 95 volts has arced over to the low voltage circuitry, and this circuitry resistors is connected to these two chips. This one I have a suitable replacement anyway, so that is not a problem. So can we test this op amp with our multimeter, for example, to see whether it is faulty or not? Well, let's have a look. I have the multimeter in diode mode, and you can hear the bleep and see the inset picture there. I've also upgraded my webcam again, so let me know what you think. The way to test these normally is to connect the red meter probe to the negative supply, and the op amp, there's two in here, so this will be input output. These are probably input output or input output, and each of these will have a reverse biased diode to ground or to the negative supply. The inputs should both be the same, the output would be different. Now in circuit it may be difficult to tell because there's other components around here. And on pin 1, which I believe is the output, I see a low reading. Pin 2 reads quite a high reading. Pin 3, well, doesn't read anything. And then on this side, pin 5 is like a diode junction, which is what I expected. That's an input. That's a diode junction, but it reads differently. And then this is the output, which reads completely different from that one. Almost all, if not all, of these dual op amp chips will have this pin out. So this is the V plus positive supply, V minus negative supply or ground, and then we have op amp number 1, two inputs, non-inverting and inverting, and the output, and then again for op amp number 2, two inputs, non-inverting and inverting, and the output number 2. So they will all follow that particular layout, and internally they will have these reverse biased diodes on the inputs, which is why we were seeing a diode junction from these two pins and these two pins when we put the positive lead to here. But this, although it's a fairly good indicator if it reads as I've just shown you, and I'll show you again in a minute, it's not an absolute indication, and you can't read much into the actual values you see in diode mode. Let me show you. Here we have the two LM358 chips from different manufacturers. We'll just put the meter back on so you can see it, and let's have a look what we've got. So first of all, we'll do the Texas. So as before, red lead to the pin 4. The two inputs, we should see a diode junction. Okay, 685 678. And in this case, we see a diode junction for the output as well, 693. Let's look on the other side. 679, 685, 693. So they read very similar to each other. The two outputs are basically the same. The two non-inverting inputs, or inverting inputs, whichever way around they are the same, and the other two inputs are basically the same. So that is, again, probably a good chip, but the readings themselves will not mean a lot. Let's look at this one. Same chip, different manufacturer. Okay, input diode junction, but it's used a completely different reading. And the output 670, output 671, and the two inputs 730, 740. So again, that is probably a good chip. In fact, these are new chips, so there's no reason to expect that they are anything but good chips. Okay, so we need to take our chip off the PCB to test it. We'll test it with the multimeter, and then let's have a look to see if we can find a better way of testing these more conclusively. Here is the op amp from the PCB. So let's try this one. Ground, or minus V. This is an output. Okay, and that's reading open. Let's look at the output on the other side. Well, that reads open as well, so it doesn't really tell us anything. I don't have any more of these to compare with. So look at the inputs. Well, that reads open. Meter is working, I'm double checking. That reads open. That pin actually reads like a diode, and that reads open. The fact, I will just double check the pin out for this to make sure I'm right, but the fact we have one diode junction on that input and no diode junctions on any of the other inputs makes me suspect strongly this chip is faulty. Let's find the datasheet, BA4560. Here is the datasheet for the 4560. Do we have a pin out? No, or do we? Yeah, we have a block diagram. It's given us a pin out here. So 1 and 7 are outputs, as I expected. 2 and 3 are inputs. 6 and 5 are inputs. And as you've just seen, only one of the inputs effectively reads a diode junction with a red lead to the negative supply. Using the multimeter, it's fairly obvious that this is actually a dead op amp. But I thought, you know what? It might just be interesting to build a little op amp tester for single and dual op amps, and maybe quad ones as well. I had a look on AliExpress, and you can actually buy these things. I will show you. I found one on AliExpress. This tests for single op amps and dual op amps. You can see the little circuit board here, the two sockets for the op amps to put in. There are no doubt ones which do quad op amps as well. This one actually does quite a range of them. It explains how it works, and it appears this is actually doing what's called a conversion test, so it actually makes a better test than you would expect from some of the little circuits that you find on the internet. It says, for example, it will test if low speed chips are pretending to be high speed chips, are they fake. So this sounded interesting enough to have a play with. I've ordered one. You can see that it cost me a little bit over €10, and that will turn up sometime in the new year. But I really want to test our op amp, although the multimeter is telling me it's faulty. So of course, what's the next best thing I can do is have a look on the internet. I had a bit of a look around, and there were quite a few circuits for testing op amps. Some of them actually contained op amps as part of the tester, but I found this one. I'll just turn that music down a bit so you can hear me. But basically this is a little tester which does single and dual op amps. They're saying that if the lights don't flash, it's bad, so this is a bad one. And in a moment you'll see him put a good one in fact, no, he hasn't, he's just showing you the pinouts. So these are the type of op amps it will test, and this is the schematic for the single op amp tester. Now, I found this a little bit difficult to quite figure out exactly what it's doing. And if we go a little bit further in, we also have a similar diagram for the dual op amp tester. You'll have a look. On the dual version, it uses 4 diodes, 1M40001, very common. The single tester only uses 2. This effectively is 2 of the single testers in one. So each tester, if you like, has 1, 2, 3, 4, 5, 6 resistors, a capacitor, 2 diodes, and an LED. This capacitor is just across the power supply. It'll work from 6 to 12 volts, single rail. So it should be very easy to build one of these. I'm sure of the components. Look, these are all 10k resistors, a 4.7, a 1k, a couple of LEDs. These are 1 amp 50 volt diodes. I'm sure anything would do. 10 microfarad. He's using 50 volt capacitors, but I think, well, anything from like 16 volts upwards will do, and a couple of LEDs. So I'm sure all of you could build one of these out of bits lying around in your components, stash, or even in the junk box, yeah? So let's see if we can actually build one of the testers for both the single and the dual LEDs. Obviously it won't do the same sort of test that the one I ordered for €10 will, but I think you could probably build this for almost nothing, and we all like that, yeah? Let's have a go. The first thing I decided to do was to actually work out what the schematic was for this. That will make it easy to build. This is an op amp, a dual op amp in an 8-pin package, very common. I think they're all effectively connected the same way. I kind of got it wrong then realised. So this is op amp 1 or A, this is 2 or B, and we have non-inverting inverting input and output, and then we have non-inverting inverting input and output, and that's a fairly common package. So I drew that, and then I started to look at that diagram and work out what connects where. And you can see I made a few errors in it, but basically I drew the op amp chip and kind of worked out power, ground, and how it effectively connects together. And I realised that that's a bit messy, but I could kind of see how it was working. So normally if you're doing something like this, you'll probably have to draw it several times. So that was my first attempt. I then didn't bother to draw the other half because it's the same as this half. I then had a look a little bit further. So I drew it like this, and this is starting to look a lot more like a schematic. You can see I made a mistake here. I had to change it, figuring out where the power pins was. So I'm getting what looks more like a sensible schematic. And from that one, I basically went to my third effort. And now I have it right, I'm pretty sure. And I think we can kind of see how this works now. It's some sort of oscillator. We know that because this flashes on and off. So you have the non-inverting input here, and via the two 10k resistors, which are equal value, this forms a voltage divider. So the voltage here will be half the supply voltage because the resistors are the same value. So that goes in on the non-inverting input. The inverting input is coming from here, again from VCC, but we have a capacitor in the circuit. So this will effectively charge up and it will delay the change in voltage. The output also comes back to the input, So when this initially is higher than this one, I think, I haven't really tried it, the output will switch high, which will take this one even higher, but it also, via this resistor, affects the charge in the capacitor, and that must affect the charge back on this pin. So I'm pretty sure that's why it's oscillating, and it's probably oscillating to do with the value of this capacitor and the value of this resistor. But I don't know the circuit exactly. I'm not an expert on op amps, but I can see it's an oscillator. So we have a circuit diagram. I'm sure if I build it, a little bit of measurement, we can do more. These two diodes clearly are stopping the difference between the two inputs being more than 0.6 of a volt in either direction. Whether they do something else, yeah, maybe. I'm not a circuit designer. So I have it there, and then the other half of the op amp, which is inputs 2, 3 and 1, just repeat the circuit. Instead of using 7, 6 and 5, it's 1, 2 and 3. And we just build it again. So that's how the dual op amp circuit works. After that, I then figured out the pin out from the single op amp, because I don't know this one really off the top of my head. I know that one because I see them more often, I would say. So I figured it out again, how the op amp is wired up. And because I knew how this one went, I kind of came with this. And it's the same circuit. I'm sure it would be basically the same circuit with the feedback here. This controls the output, flashes the LED, the charging capacitor. It was a little bit messy because I had the ground and VCC and these resistors jumping over. I wasn't quite happy, so I drew it again, and this time I have it. And it's the same, as you can see, just different pin numbers. So we know what we have to build now. I'm happy to put this together on a bit of Vero board. I won't bother with breadboarding. I've seen it working on a video. I'm confident enough it will work. All in all, we need 4 10k resistors plus 4 for each half of the other one. Yeah, that's 2 of these basically. So we need 12 10k resistors in total, 4 for each one. We need 3 of the 1Ks, we need 3 of the 4K7s, we need 6 diodes, and we need 3 capacitors and 2 IC sockets. So that's not going to be a big consideration. You can probably build this for nothing. The only thing that might cost you any money, I guess, is probably the IC sockets. Now let's work out what size piece of Vero board we're going to need to build this on. The easiest way to do this, probably, this is a single IC test version. We have the IC socket, which spans over 3 lots of holes basically. So we can say we have 3 there. All this circuitry is on the left hand side, pin 2, pin 3. How many holes do we need? Well, it depends on how many components are attached to that line, and this is the most. So we need 1 hole for this, 1 hole for the resistor, that's 2. We need 3, and then we have 2 more resistors, 4, 5. So we need effectively 5 holes to this side of the IC, and on this side, well, we have a resistor coming back round, so that's 1 hole, that's 2 resistors, so that's 2, 3 holes. So we need 5 that side and 3 this side. And then above and below the IC, well, effectively we have, from the output we have, this is a track above the IC, so that's 1, that's 2. And we also have to bring this resistor up and then across through a track basically. So that's 3. 1 if the resistor was there vertically, 1 for the resistor run across, that's 1, power 3. Yeah, 1, 2, 3. And then the other side we need 1, 2 holes, and again we have a resistor coming this way, so that's 3. So we need 3 holes above, or 3 tracks above and below the IC. We need 5 holes this side and 3 that side. So effectively from the middle of the IC 5, 3. These are holes, and then above this way 3 tracks, 3 tracks. That's big enough to build our project. That's the way to do it, guys, unless you know better than me. Okay, I just made that up as I was over the years. Yeah, let's do the same thing with the dual one. Well, we know already that this side of the IC is going to be 5 holes. It's the same circuit. Yeah, so from the middle of from the IC, if you like, we have 5 holes. Okay, but this is on the same side as this is, so we also need to put these in as well. So from the output we have 1, 2, 3 holes wide, and then that'll come 2 down. So we need 5 plus 3 holes. Yeah, we might make it smaller than that, but we can definitely build it on that. A bit of trickery pokery and stuff. Yeah, we might make it a bit smaller. So we want 8 holes this side, and then we have the same repeated on the other side of the IC. So that side we also need 8 holes plus the 3 for the, is it 3 or 4 for an IC socket? 4. So in total we need 8, 12, 15 holes wide. And then above and below the IC, well, let's have a look at it, because it is slightly different. This is on the same side, so we need above 1, 2. The resistor's on the same side, so we don't need to come across, and the same with this resistor, we don't need to come across. Yeah, it's right by the pins. That one might need a track, so let's say 3 up that way above the IC holder, and then down below it, well, we just need 2 plus the length of the, these are tracks, sorry, tracks, yeah, plus the 4 for the IC holder, 1, 2, 3, 4. So the height of this is going to be 7, 8, 9 tracks. So 9 tracks by 15 holes. So we have a good starting point. Adding in the 4 tracks for the IC holder, the single IC version is going to be 10 tracks high, and adding 4 holes across for the IC holder again, we have 5, 9, 12. Okay, so 10 by 12, and then the other one, the dual version, is also 7, 8, 9 tracks high actually. So 19 tracks we need, and this one is 15 wide. So these boards, we have 1, 2, 3, 4, 5. Well, in fact, they're actually marked with letters rather than numbers. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So it should come, and let's draw the lines on them. Let's see if I worked it out right. Okay. So it should end up by cutting this track. Okay. And wide should be 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 13, 14, 15. So cutting this track. Okay. So that's basically the size of the tester. We also note from this that on the dual version and on the single version we need 5 tracks either side of the IC holder. So 1, 2, 3, 4, 5 is enough. The IC holder can actually come in here. 1, 2, 3, 4, 5. IC holder can come in here. 1, 2, 3. The other side of there. 1, 2, 3, 4, 5. Yeah, exactly 5 each side. And we can also work out the positioning of them. So the first one needs 3 tracks above. 1, 2, 3. Our IC holder at the top is going to be there. Okay, it's going to go 1, 2, 3, 4. 1, 2, 3, 4 holes. It's going to go in there. Then we need 3 tracks below. 1, 2, 3. Then we need another 3 for the dual one. 1, 2, 3. So 1, 2, 3 again. So the other IC holder will go here. And then we have 1, 2, 3 tracks below. Okay, let's stick the IC holders in there because I'm quite confident I've got it right. And once the IC holders are in place, it's going to be easy to solder the components around them. Let's build the single one first, and then we can figure out if all that effort was worthwhile. I have some 8-pin IC sockets, or DIP sockets they're called, dual inline pin, but I don't have many of those left, so this is just a good bit of advice to you. If you find you're running low on something, now is the time to order some more. Yeah. So I had a quick look on AliExpress. I can get 100 of this size for €1.30 plus €2.40 postage. So we're looking at €3.70 for 100. So I will add them to the cart right now. I won't buy them just at the moment because I'll just wait till I get an order together, but they won't get forgotten now. The next time I place an order, when I have a few more things I want, they will be on there. I don't need them now. I have a few more left, but yeah, if you don't do it now, guys, you'll forget and then you'll realise when you run out. Useful tip, I thought, guys. No doubt you will think, yeah, Rich, that was really a good idea, and then you will forget or not do it, and then don't blame me when you run out. Yeah. So we can put these on here. We have pin 1 to the top. I'm going to put them the other way around, actually. I'm going to build it this way. Just get them in the right place. Exactly there, so we can solder this one in and then do the other one. If I try to do them both at the same time, no doubt they will fall out before I can solder them. I should probably clean that blue ink off, but I'm not going to bother. A little bit of flux and it will soon disappear when I put the solder on. Yeah, I'm sure of it. So IC socket in place. I'm pretty sure I can solder over this. Just make sure it's sitting flat, not quite. So now's the time to straighten it up. I'll clean this mess off when I've soldered it. I don't think we'll end up with blue solder. Okay, clean that up. But before I do, actually, I'll fit the other socket. And now let's just build what we see. So I'll start from the left hand side, moving over this way. This is the single tester. We'll use this one. We could use either. So we'll just build it as we see it. All the parts are new, by the way, apart from the 10 microfarad capacitors are poles. So I've tested those with my capacitance meter and they're okay. All the rest of the components, I'm just going to trust them. Okay, so one diode in between 2 and 3, one going the opposite way, so we can put those in, opposite polarity. And then I'll just work my way across. I've put the 2 diodes in and the 2 resistors onto this pin, so the only one remaining from here is the 4K7 coming across to the other side and the 10K coming across to the other side. But it's probably easier if we build this part of the circuit next, yeah, and then we will know exactly where we need to put the 2 resistors to and they'll go to the correct track. So let's build this little bit of it next. Okay, I've built this side as well. I just checked the LED with my multimeter on diode mode to make sure it's the right way round. It lights up with the red lead on the positive terminal, so that's correct. So really all we have now is these two resistors to put in. One of them comes from pin 3 of the IC, and we have a spare hole. In fact, we have two spare holes, and we need that to drop that down to this unused track which we have running along here, and then a wire link back up to pin 6, and the same with the other one, goes from pin 2. Okay, and we need to connect that to the track which is connected to the bottom end of this capacitor, and there it is. This is the resistor from pin 3, the 4.7, which comes to this track you can see running along here under the resistor to this jumper and back to pin 6, and this is the other one from pin 2 which goes to this track which goes to the junction of the capacitor in this resistor. I could have put this resistor across here flat on the board and cut the track and then put a jumper in where the resistor is now, and the same with this one. I could have put it in here flat and then put a jumper from here to here. I would have had to put two cuts in the board under the resistors, under the tracks. The way I've done it, it requires no cuts apart from under the IC, which I think is quite elegant. But if you prefer not to have these sticking up a bit, you could do it that way. I've put it in such a way that even if it gets knocked over, it can't touch, like for example the end of there, so it's fine as it is. All we need now is pin 4 to the ground and pin 8 to the supply, which is actually, oh, I misjudged the capacitor. It's one track higher than that. I might just move this down one actually, and then that will be the actual 5 volts or 9 volts, whatever we're going to use. Then let's test this circuit to see if it works. That means I have the schematic right, and if it does, we know the dual version will also work. So I'll just put this one back to there, and then we can power it up and we can try it, obviously connecting 4 to there. I've noticed, and it's not a problem by the way, when I first worked this out, I actually had 1, 2, 3, 4, 5 tracks, and then I accidentally put the IC socket on the 6th one, so I actually calculated it exactly. These are just some little pin headers, power and ground. These two are connected together. I find quite often if you put one pin header in it, the track breaks away the other side. If you put a pair, they tend to stay in place. So we can attach the power to this. We'll test this one. If it's working, then we'll build the other one, which is basically just 2 of these. I have the power supply on 9 volts, near enough. I can attach power to the board. Power, ground. And the LED comes on by itself. Let's see what happens when we plug our op amp in. So this is a 741 op amp, single op amp. Well, it's a good op amp. At least I think it's a good op amp, but it's not flashing. I wonder why. The reason it's not working is fairly obvious actually. We have 9 volts coming in. There's the 9 volts. The 9 volts then goes to the capacitor through a 10k, a 1k, the LED to ground. You would think that because this capacitor blocks DC, there would be nothing coming through here, yet the LED is lit fairly dimly. So it seems like a little bit of current is passing this way. We can actually have a look. So we can go to the 10k resistor, and we have 2.379, and the other side 2.017. So we can actually calculate the current flow, and I've just figured out there's actually another way that the current gets here. I better show you on the schematic. So here is our schematic. Now we don't have the IC inserted, but we have some current paths. This will block DC, or it should if it's a good capacity, so the current cannot flow through here once it's charged up and down through the LED. But where the current can come is this. It can come through the 10k, through this diode that's forward biased, through the other 10k, through yet another 10k, and through the 1k to ground. So that's where the LED is getting its current from, through 31k. The reason it's not working, and when we put the IC in, nothing happens yet, is because this doesn't have any power. And it doesn't have any power because I forgot to connect pin 7 to 5 volts. So this is the ground, 0. This is pin 7, should be power. And you see there's like 1.6 volts on there. So that's obviously leaking in somewhere, but I'm not particularly worried where. This chip does not have any power. So let's connect the power from pin 7 at 9 volts. I've put the wire link in now, so pin 7 is the power on these. A little bit unusual layout maybe, but obviously they thought it was a good idea. So I've put the power back on. The LED is lit dimly again, but we know there's a path. So from ground to pin 7 now, we have 9 volt supply. Let's see if it works now when we plug our chip in. Yeah. So in fact it fell back out again. So that circuit works. Good chip LED flashing. Now we can build the other circuit. I've built the dual op amp tester. This side I had drawn the schematic. This is just a mirror image. So effectively, as I built this side, I built this side at the same time. Practically the mirror image of it. I had to move a couple of resistors around to get the space to put this one in. So I actually used all of the tracks on this side, which is one more than I originally thought. And you'll see on this side, I ended up using 2 more. That's the original length that I thought it was going to be. I actually have 1 empty track there and 1 there. So I could have actually made this 2 tracks shorter that way. And the original marking is a bit faint, it's rubbed off, but the original marking was here. And I actually ended up with 2 tracks wider. So it's still fairly small, but if you make one, if you refer back to the video, it's 2 holes longer that way, and it can be 2 tracks shorter that way. Now let's try it. I have some good op amps here, dual ones. That's the one which we're pretty sure is faulty from the multimeter, but we're going to prove that. Again, we'll attach the power from my bench supply on 9 volts. This would obviously run very nicely off a 9 volt battery. Let's switch it on. And all the lights come on dim, which is a good sign. This is a 4558 op amp, common one. So let's plug it in. And both LEDs flash, okay, so that's a good one. We know the tester's working. What else do I have? Is it the same sort? I think it's an LM358. Yeah, this is an LM358, a Texas one. Both LEDs flashing, it's a good one. We have 1 more LM358. Again, both LEDs flashing, it's a good one. You don't even have to push these in hard, you just rest them on the socket. And then we have our suspect, the one that looked like it was faulty on the multimeter. Let's have a look. And it's Duff, yeah, it's a faulty one. Both LEDs are on. So we know that is now confirmed to be faulty. There we have it then, guys. It's working fine. But just before we finish, let's have a look at what is happening with this on the waveform on the scope. I did mention I was interested to see how this works. So I'll put the single op amp back in here and let's have a quick look. This is the LM741 then, single op amp. I'll use the dual beam scope. Somebody commented that really you need a dual beam oscilloscope, dual trace, for any sort of repair work, and I said, well, you know, actually on the channel I've never had to use dual beam, although 4 of my oscilloscopes have it. And now I'm actually going to use it, yeah, 1 or 2 videos later. So let's have a look. I've set the oscilloscope to twin trace and dual trace. Let's have a look on the output of the chip. So this is the output. And we can see we have a nice square wave, obviously a low frequency, 5 Hz. It's flashing the LED and it's nicely triggered. So now we can actually have a look at the inputs as well to see what is on them. So pin 2 is one of the inputs. Yeah, and that's, I assume, coming from the capacitor. And what's on pin 3? Similar. I was hoping I might be able to try and figure out exactly what this is doing. Let's look at the 2 inputs. So we have pin 2 as an input. Okay, we have pin 3. What can we see? Well, it looks like, yeah, you can see it now that the yellow trace and the blue trace at the bottom end are crossing over, yeah. And I'm guessing, well, a bit of knowledge tells me that's what's actually causing the output to switch when the 2 cross over. 3 traces might show us, but that's obviously what's happening, that the 2 inputs are crossing at the bottom end. So effectively the yellow is going lower than the blue one at that point, or cyan at that point, and that's what causes the output to trigger. And we get a square wave. Okay guys, so that was interesting. That gives some idea of how this actually works. I hope you enjoyed that video, guys. I clearly need to order some of the 4560 ICs to complete that repair, with it being an amplifier. Okay, it is the power supply section and the thermal detection section, but the customer isn't particularly desperate to get this back. They rent these out, they have quite a number of them, so he won't mind waiting while I actually order the parts. So I'll get the correct op amps rather than mess around trying to put something else in. On the next section then, we can replace the faulty chips and we can repair the actual damage to the burnt section of the PCB. How I will actually do the repair, I'm not going to try to fix this part of the PCB or even to use it. We have a 95 volt supply coming down this burnt section, and it goes off over here effectively down to the end of the board here. One end goes to this pin of the 95 volts minus supply, and the other end goes to this resistor. So I'm actually going to cut the track at either ends. It doesn't go anywhere else because I've followed it all the way down, and I'm going to connect a wire from there to there. That removes that, because this is probably going to be conductive now. It's like charcoal. The 3 resistors that burnt, 2 of them actually connect from the ends of these resistors. This is the ground and the plus 17, I believe it was. And the other end of the resistors go to the op amp. We have the schematic, so I'm actually going to connect these resistors, one end to here and one end back to the chip where they're supposed to go to. It was this one or this one. I think it was this one. So those resistors I will literally strap over to where they go, ignoring this section again. And the same with the other track which went that way. I shall just cut it off, and where it goes I shall just make it up. And then there was one more resistor, and again I know where it comes from in the schematic, and I know it actually goes to this end of this capacitor, and that's also connected to there. Again, I'll make sure it's all isolated from this section of the board. So I'll replace the components literally by jumping over this section without putting anything back in here, and then hopefully with the 2 chips in, this will work. When the parts arrive, we can get on with this. We have a plan. We also now have a single and dual op amp tester, and we also know how to test them with a multimeter. Quite evidently from this fault, the Multimeter told us that chip was faulty, and that chip was faulty. I'm very interested to look at the commercial op-amp tester to see if that is better than this. It apparently has more facilities, if you like, or it tests the chip in a better way. So that's already ordered. That will be yet another video. And I hope you enjoy what we were doing today. So I will see you all soon on another Learn Electronics Repair video. Ciao for now, guys.